This is Venkata. He is a staff software engineer at Juniper and has traveled to us today from Sunnyvale, California. This is Venkata's first time presenting at NANOG, and it's a pleasure to have him here speaking with us today. Welcome.
Thank you. Thank you for that introduction. This is my first time at NANOG, and I'm very excited to be here. Before I begin, I would like to thank my fellow collaborators, Kolby Barth, Krishna Karthik Gadiyaraju, and Vishnu Pawan Biram. I would also like to thank Rajat Setia and my shepherd, Steve Plot, for their guidance. So let me give you a brief introduction into the topic and then take a deep dive into it. So we all live in the era of 5G, and we are surrounded by numerous services and applications. These services demand a vast amount of bandwidth, and accurately assessing these bandwidth requirements has become a challenge for all the network operators. So bandwidth management is, at its core, involves monitoring the bandwidth throughout the day, week, month, or the year. And it helps network operators plan their design the network for optimal performance and growth. One of the most well-known solutions for bandwidth management in the traffic engineering space is auto bandwidth. So what is auto bandwidth? So on every networking device, there's a certain routing process that collects traffic statistics corresponding to all the tunnels. And auto bandwidth solution automatically adjusts the bandwidth allocation based on the volume of traffic that's flowing through these tunnels in real time. Now, let me get further into the details, the what, the when. So what bandwidth to adjust to? So the auto bandwidth solution uses a computation that we call maximum average, which is computed as the maximum of the sampled byte rates from the previous interval. The next logical question that comes is, when do we adjust such a bandwidth? Now, this is determined by something that is termed as adjustment interval. The auto bandwidth solution adjusts the bandwidth periodically at the end of every adjustment interval. Now, unless overflow or underflow are provisioned. So what is overflow or underflow? So if the sampled bandwidth exceeds the current bandwidth on the tunnel by a certain threshold, a certain number of times, it is deemed to be an overflow. And if it falls below the current bandwidth by a certain threshold, a certain number of times, it is deemed to be an underflow. And when underflow or overflow occur, the bandwidth, the adjustment interval is preempted, and bandwidth is adjusted on the LSPs. Now, in a regular scenario, once the adjustment interval expires, the bandwidth is adjusted if the computed bandwidth exceeds the current bandwidth by a certain threshold, also known as adjustment threshold, and new paths are computed to check if resources are available. Now, if resources are available, the tunnel is resignaled, and new tunnel is established with the computed bandwidth. Now, this solution looks good in theory and works well in certain scenarios, but there have been some well-documented struggles with respect to provisioning features for auto bandwidth, such as overflow, underflow, and myriad of other features that are provided by vendors to get an accurate adjustment bandwidth and tune it in such a way that the solution works really well. And we have also seen numerous requests from network operators to go a bit faster than what is supported currently. This is not possible with the current auto bandwidth solution, partly because the current auto bandwidth solution is reactive in nature. If you look at the plot to the right, we see that the auto bandwidth solution using the max average computation adjusts the bandwidth from the using the maximum of the previous adjustment interval for the next adjustment interval, which causes a certain certain inconsistencies in using the network resources. So there are many interdependent knobs, as I mentioned earlier, to get this to get the current auto bandwidth solution to work accurately. With that said, this gives us the motivation to come up with a brand new framework. Now, we want to proactively predict the future bandwidth by treating the bandwidth calculation as a time series forecasting problem, using the trends and patterns in the historical bandwidth values. Now, this approach can help in allocating the bandwidth faster compared to the current solution, since we predict the values using historical traffic trends. We would also like to build a data-driven solution by leveraging real-time statistics, real-time data that are streamed today at a higher frequency. And this enables the machine learning based solutions to be able to cater to shorter historical windows as well. The other goal that we set out to achieve was to build a low footprint approach by reducing the operational overhead and make sure that we make minimal changes to the network to the network design. Now, we have spoken about treating bandwidth calculation as a time series forecasting method. Now, time series forecasting is quite popular in throughout our daily lives. We have seen time series forecasting being used in weather, predicting the weather, to stock market, to retail sales as well. So, what is time series? So, a time series is a series of observations that are taken at specified times at equal intervals. Now, it can be used to predict future values based on historical traffic trends using some machine learning models or time series models. A time series can be univariate or multivariate based on the number of variables that we observe. And a time series exhibit a lot of properties, couple of them being trends and seasonality. That is, the data can exhibit an increasing or a decreasing trend or no trend at all. And the data can repeat itself over a certain period, which can be leveraged for time series forecasting. Now, sometimes it is possible for that data can exhibit trend and seasonality together as well. And since time series forecasting is popular, there have been quite a few number of methods that are available today that exploit patterns in the data to predict future behavior. There are also some regression-based methods as well as deep learning methods that are available. Now, with these goals in mind, let's look at how the bandwidth forecasting has evolved. So this particular framework can be algorithm agnostic. So we can leverage any of the machine learning, deep learning, or statistical methods to predict future values. This is applicable to any technology area, and any type of traffic can leverage this particular framework. Since we treat this problem as a data-driven solution, this particular solution framework can be used to leverage to monitor the network and using applications such as health monitoring. And this framework is lightweight to be able to deploy anywhere, and with minimal set of configuration changes to the device using microservice based architecture. Now, we have seen the overarching application framework. Now, let's look at the building blocks of such a framework. Now, obviously, there will be a network device or a set of network devices that stream telemetry data or data from out, and there needs to be a collector that collects this data and stores that data in a database. There also needs to be an application which hosts the machine learning models, which processes this data and comes up with a prediction. And there can be an action policy engine that decides whether to feed this back to the device. Now, all this information can be visualized and logged for network operator use. This particular framework allows for network operators to run in monitor mode to validate the performance of the machine learning models, or flip it to active mode to adjust the bandwidth on the device and complete the loop. Now, this framework is modular in nature, so it allows for plug and play at all the building blocks, and of course you can we should be in a position to add any other building blocks to this framework as well. So we'll revisit this framework at the end to identify a couple of applications that can leverage this framework. Now that we have seen the building blocks and the framework for bandwidth forecasting, let's look at the logic that typical bandwidth forecasting application can follow to come up with a prediction and solve the problem there. So once the data is collected in the database, this data is fed to the machine learning models for training. So the models are trained continuously. We have the ability to use an ensemble of machine learning models as well. And these models are trained continuously, and it is important to test if the models are performing well. So the models are tested, and once we at this point, if we have an ensemble of models, we can select the best model that gives us the best prediction, and use that value to adjust the bandwidth on the device. So in the example below, we see we have used a 300-second adjustment interval, and we train the models using data from the past two adjustment intervals as well as a chunk of data from the current adjustment interval. Now, the data collection and training is happening periodically throughout the application life cycle, and the models are also tested continuously. Now, if you look at the plot underneath, we see that the forecasting models make a prediction at the middle of the current adjustment interval for the end of the next adjustment interval. That is, based on the previous data, it predicts that the bandwidth would be at the black line at the end of the next adjustment interval, and the models are continuously tested in the test period. Now, from the example, if 95% of the traffic is covered by the model's prediction, and the predicted value exceeds the adjustment threshold, which is 10%, in the example here, we select the model with a higher prediction to adjust the bandwidth. If none of the machine learning models cover 95% of the values, we can always fall back to the maximum average computation. And as you see underneath, the maximum average computation happens at the end of every adjustment interval. So it's important to note that the values in blue are all configurable parameters. It's up to the implementation to modify these parameters. Now, one of the properties of machine learning models is or the forecasting models is they tend to identify if there is a trend or a pattern in the data. As we see in the example here, the machine learning models prediction in the black tends to have identified that the bandwidth would be at the black level at the end of the next adjustment interval. But since max average is a computation that follows the maximum from the previous adjustment interval, it tends to miss the increasing trend. Now, in general, machine learning models tend to recognize trends or patterns, and when trend or pattern appear together. Now let's take a look at the machine learning based forecasting in action. Now, since it's important to track all the metrics that correspond to such a solution, such as what data is being collected, the time it takes to train the machine learning models, what is the best model and the bandwidth that we use to set or the bandwidth that we have selected corresponding to the best model, as well as the error corresponding to each of the ML models, each of the machine learning models. Now, all these metrics are tracked, can be logged back, can be logged in the file, or can be written back to the database for visualization in the future. Here we see at the bottom we see such an example of all the metrics being tracked in a log file. Now, the most logical question that everyone would ask is machine learning based forecasting better? Now, based on our experience, we have seen that the machine learning models are less susceptible to outliers than the max average computation. As we see in the plot on the top left, the maximum average bandwidth actually adjusts the bandwidth for the next adjustment interval because of a spike, because of a single spike from the previous adjustment interval, which may lead to inefficient use of the network resources. And because of the fact that machine learning models are less susceptible to outliers, the error of the machine learning models is significantly lower than the max average, which tend to explain that the machine learning model prediction is much closer to the actual traffic than the max average computation. And the bottom right plot shows the coverage percentage of all the traffic, and we see that the machine learning models tend to cover more or less same amount of traffic compared to the max average, but with a lower error. Now, in general, machine learning models tend to perform well when there is patterns in the data. Now, to summarize, we have seen how the machine learning driven application forecasting framework leverages real-time data to enable proactive bandwidth which enables proactive bandwidth forecasting by exploiting data from the historical patterns, and it allows for faster adjustment of the bandwidth, which was one of the goals that we set out. And since we offload the bandwidth calculation out, it saves some precious CPU cycles on the device. Now, let's circle back to the application framework to identify a couple of applications that can leverage the framework. Now, this is something that we call real-time insights. So, once the data collected from the device or the devices is stored in the database, this can be visualized, and real-time insights can be drawn into the traffic behavior using statistical methods. This actually gives the network operator this serves as a tool for network operator to plan for the future based on the data that they have collected already. And this is the second application that we have identified is something that we call configuration evaluation. Now, this is something that a network operator can use to make changes to the configuration on the network device and collect the data and have the data processing pipeline process it and come up with a value. Now, it's up to the network operator to decide which configuration performs the best and make a call as to which gives the network operator the best efficiency. And based on the most efficient performance, they can always go back and provision their devices with that particular configuration. Thank you. I do have a demo for this solution, and if anyone is interested, they feel free to tap me on my back. Thank you. Yeah.
So when do you think the system doesn't perform as expected? Do you see a correlation in or an inflection in drop packets as the system is training itself? And second is, do you think a network-centric view would be more useful, especially when you have tiered deployments, when network operators, let's say they purchase a Juniper box, but some other vendor does not have this. So how do you train systems which are asymmetric? For example, it's not like all systems are built with the same algorithm or will exhibit the same data patterns, right, as you test them. So each vendor is tested differently. Each network is built differently, right? What are your recommendations on a mixed test and analysis scenario?
Yeah, so the solution can be both distributed and centralized. If it is distributed, you particularly cater to a certain devices in your network, and if it is centralized, it's possible for you to collect the statistics from all the devices in the network and correlate that with something like traffic engineering database to sort of make a call at the centralized network, centralized location, and then feed it back to different devices. And of course, traffic patterns are different on every device, and it's up to the machine learning model that you pick to sort of and the model that you train and predict to come up with with an accurate value to feed it back feed back to the device. I hope that answers your question. If not, I can definitely circle. Oh, drop packets. Yeah, and that's a totally different. I can get back to you with that. There is a different proposal for that. Yeah, I can get back to you.
Do you have any thoughts on or plans for integrating this into a routing protocol that's like operating on a device such that the path that traffic takes is updated live?
Yes. So yes. So it's again depending on the types of models that you use and if your device is capable of handling the machine learning model training and inference on the device, this can definitely be deployed onto the device, and this can definitely replace the traditional max average solution. It depends on the compute that you have on the device. Yeah.
Excuse me. Two-part question. In the modeling that you did you see any, like it looked like the ML, like the model-driven approach yielded a lower required bandwidth requirement. Did you do like network-wide modeling that gave you an idea what the kind of like increase in additional capacity network-wide might be?
Could you repeat the second part of your question?
I guess the first, well, two questions rather.
Yeah.
This looks like a very LSP-centric perspective on things in
Yeah.
terms of like auto bandwidth adjustment.
Yeah.
And it looks like it yields a a lower bandwidth requirement more broadly relative to max average. I
Yeah.
guess I'm curious as to whether you saw a net improvement in overall network capacity across folks who are doing multiple parallel LSPs to a common destination or something along these lines, so that you're improving bin packing overall.
Yes, we did see a significant improvement in network capacity because of the fact that machine learning models tend to predict the bandwidth much closer to the actual traffic. Compared to max average, which again reacts to the spikes in data. If there is random data and if the data is spiky, I'm pretty sure both the models would do pretty much the same. But because if there are trends and patterns in the data, I'm pretty sure the machine learning models can.
And so the next question is specifically focused on the models. Do you see a mechanism for operators to be able to inspect or understand what the models are doing, or what the inputs beyond the training on the models are, and how do you see those being exchanged or shared?
All So we have built a solution on this, and what we do is we take all the metadata corresponding to the training and prediction, and we write it back to the database for visualizing later. So that can always serve as the source of truth for the network operators to understand if the machine learning models are performing well. And we do have something called a monitor mode. If I don't know how to go back. Oh, sorry, it's close. Okay, we do have something called a monitor mode for network operators to see how the machine learning models are performing, and make a call whether to start making the adjustments back to the device and by flipping to update mode. So all those provisions are in place, and you can always visualize the data that's coming out of the machine learning models as well.
Hi, thank you for the talk. Out of curiosity, 2 questions. I'm
Sure.
wondering, of the machine learning algorithms, was regression or deep learning approaches, were any of them more performant? And the second part is, I'm speculating that you're running inferences and training quite frequently to model this data, but I'd like you to kind of expand on how often that actually is running.
So can you repeat your first question, please? I can answer the second question.
So in terms of the actual model that you're using, did you notice a increase in accuracy or performance for either regression or deep learning based models? I'm assuming you're doing RNN on the deep learning side.
Yeah. So we have used multiple. We have tried multiple machine learning, statistical, some and a couple of neural networks as well. Okay. Based on our experience, it makes more and based on the data that we have collected, we have seen that the traditional statistical or the regression models, nonlinear regression models, tend to perform much better than complicated neural network that we have written. Could you repeat your second question, please? Sorry.
Sorry, the second question was how frequently are you running training on data sets and inferences?
Okay, so it again depends on the adjustment interval, or if you are trying to forecast way into the future, we would suggest to take the data from a longer historical window and train the models. If you are looking at a very short historical windows, or if you are looking for a short-term prediction, you can always train the models using the last few adjustment intervals worth of data to come up with a short-term prediction. So it purely depends on the types of models that you're using and the type of forecasting that you want. Yeah.
Robert Kishtakira, IPNCC. Very good talk. Thank you very much. I'm interested in the cost of actually running the ML engine itself. I can imagine a scenario where this is highly interesting to run per peering session, for example. And if I have hundreds and thousands of that, I really want to see if some of them is peaking or are peaking, and there's an anomaly somewhere, not in the whole system, but on some of those. So that's only feasible if the cost of doing this is actually low enough.
Yeah.
So can you address like how expensive is this to run?
Yeah. So with the advent of microservice architecture, the operational overhead for deploying such applications has come down drastically, especially these days. And GPUs are fairly cheap to install. Not that you need a GPU for this, but it's the cost of
that increases the cost, right? So
it does. But as I said, if you already have such these resources, you should be in a position to deploy this even on a virtual machine. And of course, I understand the fact that you need a distributed solution for this, and you need multiple VMs or hosts to deploy this. But yeah, you would save precious CPU cycles on your device as well. So it's a trade-off, I would say.
Fair enough. Can you state that it's actually cheap to do?
I'd leave that to the network operators. I will let you guys answer that question. But yeah, I'm a developer, so I don't have insights into that. So.
Any other questions out there? Anything online, Chris? Excellent.
Yeah.
Thank you, Venkata. Thank you.